So, welcome to Marvin from the Karlsruhe Institute of Technology. Marvin is one of the ESRs of the DIGIMAN project. Marvin, for yourself.
Thank you, Guido. Welcome, everybody. It's my pleasure to host you as the first ESR of this presentation. And to keep up the story, we will talk about semiconductor production, and in this case, in particular, about using explainable reinforcement learning for production control in semiconductor manufacturing. So just think of the wafers Christian just presented. Once they make their step into a factory that produces ICs based out of them, then we are in exactly the environment that we're looking at now. I want to take home one particular message, that reinforcement learning is a very promising and interesting technique, not only for controlling processes, but also controlling systems on a bigger level. But it's not easy, but it pays off to play around with it. Why is reinforcement learning so important? Why did it gain so much momentum? You see, there's a lot of technologies available. Reinforcement learning didn't start yesterday. It started about 30 years ago, becoming more and more popular. And it needed some momentum to tip over. First of all, it's the availability to process large data very cheaply, very easily. Secondly, it's the availability of tools that are now available, that are freely available in the sense of everybody can do that. Every one of you can take a short time to use reinforcement learning and apply it to a problem. It's not some big magic. The magic comes at the end to tune it to get the last few percentages, but in principle it's not very complicated. And we see more and more successful examples. For instance, just at the beginning of our DIGIMAN project, when 2018, not me, but everyone else was submitting it to European Commission, AlphaGo was in everybody's mind when the first best human player was beaten by a purely reinforcement learning based system. So it is a very good tool that is just at the right time around right now, so it turns off, it pays off if you have a look at it. So what is reinforcement learning? Reinforcement learning is basically learning from doing something and learning to do it better and not to do stupid things, just like a child putting its hand on a hot plate. So you learn it's hot, you better avoid that if you see that the plate is turned on. And in a similar way, there's an agent situated in an environment, which for us would be our environment, selecting an action that then turns the environment to a new state, to a new behavior, observes this behavior, gets some sort of reward, and takes another action. So a very consecutive selection of actions that we can see here following this line. So it's a chain of actions that transform the environment on the same way, gaining some reward. And can be mathematically described as a Markov decision process with a set of states. Obviously, sometimes it's hardly describable as a set. It uses a set of actions, but even that is not very straightforward to decide as soon as you leave a very simple process control. And what is most crucial, it is described by a function of probabilities, what is going to happen next. So remember the simple example, put your hand on a hot plate. There's a 100% probability that you burn your hand, so it's very easily tractable to find an optimal solution. But reality, especially larger systems, is not that easy. You can select an action, and based on an action 2 days ago, something pops up randomly. Or look at machine breakdowns. Maybe there's no connection of the machine breakdown to what you did just now, but it still turns out to change the environment very heavily. So, in order to solve this policy, a policy which we call pi, you regard the conditional probability of selecting a certain action given that a certain state is selected at the moment. What you do technically is you optimize the reward into the future, the cumulative reward. That means you have a discount. This is also another factor you should consider. If you're making your agent discount very high, then you're very short-sighted decisions. If you're making it too long, it will be very hard for the agent to learn the short-cycle effects of some of the decisions, because it's like only making strategy and not making any short-term decisions. So all in all, there's one thing that is very important about Markov decision process is the so-called Markov property. So the Markov property states that every information is in the current state. So the probability of the next state in the reward only depends on the current state and current action and some randomness selected. But it does not depend on what you have done before. And this is quite tricky because in real systems, you have many different processes running at the same time. So you need to form a formulation so that your state contains most of the information. Now let's have a look at production control and where we can apply it for reinforcement learning easily. This is a hierarchy of reinforcement learning starting from strategic production control and planning, from a strategic decision and thinking of months or years. It goes down into procurement for months and weeks. But for reinforcement learning, because you have these learning effects, these cycles, it is much more advisable to start from the bottom, some short-term decisions. So we are looking at operational production planning or production control in that sense. But how do you do that? Do you want to use reinforcement learning in the real factory producing millions? That's probably not a good idea. So we need a tool that helps us to learn and map and understand everything. And this is where we regard simulation models. And simulation model basically has the idea, looking at the real system, you form a model in the model world, the simulation, then you do something to the simulation, look at the results, and based on these results, you lead to a conclusion what you do with your real system. And this works very well if your gap between the real system and the simulation is not too big, then it is very easy for you to train the reinforcement learning agent in the simulation. Here you see some pictures from Infineon, our partner, industrial partner in the DIGIMAN project. Just let you know, there's no unpublic information here. We use the data based on available information and based on discussions, but it's generally transferable. So there's no need to worry about the data quality, but there's also no more data than anybody else can access that you get here. So you take the production system, transform it into the simulation model. The simulation model as the next step becomes your system environment. So you work in the system, in this environment, with the actions from the agent, which you then have to select. And then you have to look at the performance. Is the agent performing good or is it performing bad? And you iterate between 4 and 3 and maybe also 2 until you find a reinforcement learning agent that is behaving sufficiently good. So let's look at the characterization of the semiconductor plant. And why semiconductor manufacturing is so interesting, of course in general, but also for using operational reinforcement learning production control. Because we see a lot of up and downs in semiconductor turnover, we see in sales, so there is no stability. It's not planned over many years. It is rather like a demand curve that is going up and down, also utilization and prices. We also know that the wafer fab, we can see here the silicon wafer, for instance from Topsil, that is then put into the front-end production where the ICs are produced, then going to back-end, inspection, separation, and finally to what you can buy as a semiconductor. What's so interesting is that in this front-end, you have a multitude of processes that is used recursively because all of the wafers are built layer by layer. So they just run through the system, very convoluted, from one machine to another and build one on top of each other. So it's it's an almost chaotic system from a certain perspective if you produce this. And it has a cycle time of 10 to 20 weeks. That is several months, which makes it very hard to control such a system. So for this case, I'd like to present you a very simple case with just a number of machines connected by some material flow, and we want to control the material flow with reinforcement learning. This is the example system, consists of 8 machines in total, 3 what we call lifts. This is where material gets in and out of the system. It has stochastic failures of the machines. Their delivery of these orders and jobs coming into the fab is stochastic, it's intermittent, because if you have so many different jobs, 20 weeks in one factory, you cannot perfectly plan their timing to come every minute. They sometimes come more, sometimes comes less. And there are lots of actions that you can do. Transporting some stuff from the lift to an asset, to the machine, to perform some value creation, and then transporting it to another or transporting it to a lift. And then we looked at different scenarios. I think one of them is sufficient for us to regard at the moment. You will find more stuff in the publications or in later discussions if you're interested. But what we can see is, on the left-hand side, a very typical curve for reinforcement learning. This looks very interesting, very good. You start at a very low reward. The reinforcement learning is like the child tapping on the hot plate, then learning it's not a good idea, getting more and more reward, and then reaching a kind of plateau at a very high level. However, it's still interesting to zoom into the details. What I want you to take home for reinforcement learning, this is interesting, but actually what's really important is the other side. Look at the real performance. Don't look at the reward, because the reward is what you design. If you use reinforcement learning, you design the states, you design the action, and you design the reward. So if you only look at the reward, you can just tweak the reward to look like a very nice curve, but this has nothing to do with what you see on the other side of the performance. In our case, luckily, after a lot of experiments, we can see that reinforcement learning, the green line, is outperforming the benchmark that is currently used state-of-the-art with respect to system utilization. So if we regard this one KPI, we can already achieve a higher performance. However, this is not sufficient. As we know, if we look at production planning control, utilization is not the single most important parameter. There are also KPIs that you're interested in. So we performed another interesting task by looking at the states. In this case, a very simple state, just permissible actions. We just give the state of which action can be performed. Can I transport something to machine 1? Yes or no. Can I transport something from machine 2 to machine 3? Yes or no. So very simple information. It doesn't have all the information people look at, like when was the last failure, how long is this waiting. It's a very simple state. And we give a reward simply based on the decision if we transport something to a machine or transport something from a machine. And as you can see, this directly scales for the different KPIs. So we have the utilization in green, but on the other side, we have the waiting time. You might want to have high utilization, but low waiting time. And obviously, you have to find a trade-off between all of them. And we can at least see that reinforcement learning is able to allow you to control this trade-off. With this very simple example, just by this combination of this linear vector, you are able to control what kind of combination of utilization and waiting time, if you look at the two most important parts in operations theory, you want to achieve. So we reduce the waiting time at the cost of some utilization, and you are able to control it yourself, which is very impressive and very simple. However, in the long term, this is not enough. So as we can see, you can find a lot of other agents as well. In this case, for instance, we found a Pareto front, because some agents perform better, some agents perform less. And it's worth exploring, because now you're able to go almost anywhere on this curve. And also this curve tends to translate to different scenarios. If you can see, for instance, this 28 here is this 28. So it's the same agent in another scenario performing similarly well and pushing the boundaries of what we have seen in performance before. However, and this is a bit tricky, there is no closed form and no guarantee that not someday somebody will find something even better. But I think we're already doing quite well. So now comes another important question. I think the most crucial about reinforcement learning. You show that it's working well. You show that it's working better on average. But who's going to trust you to use the system? Because at some point, it will make different decisions. And who is willing to go that risk? And that's where we looked at explainability. I just give you a brief insight into some techniques that might be used, because I think there's still a lot in explainability, not only for reinforcement learning, but also for machine learning in general, and I'm sure we'll see more about that in the rest of the conference. So explainability for reinforcement learning, for instance, if we regard one reinforcement learner in a factory layout and compare it to, for instance, the benchmark, what do we see? We see that at some point they start somewhere, go somewhere, transport something. But as soon as they deviate once, it's kind of a butterfly effect, because how can you compare? You only compare the average after all. There's no way of saying this one is better or worse, because one of them goes left, the other one goes right, and then what? Is left or right a bad decision? Is it a good decision? We just compare it by average so far. But for people on the shop floor in the factory, that is not sufficient because you need to convince them. So we came up with a couple of measures, just the two most important ones. This is the simplest one, explain by similarity. Look at different scenarios. How similar is this? Because this is explainable to a human. Like, for instance, this is 20% nearest job first, about 5% first in, first out, and about 12.2% to the empty current state-of-the-art heuristics. This at least gives you an idea what kind of combination, like it focuses a bit, in this case, on being close to a place, like nearest job first, selecting the closest action. But that also has some look into make sure machines are not starving and FIFO. But it's not perfect, because it's again kind of an average. So what we come up with, and which I think is very interesting, is looking at saliency. Saliency is known from analysis of pictures. If you have CNNs or other large models looking at pictures, and you want to learn, like, why is this a dog? What you can do is you can find a derivative of your policy or your neural network with respect to the input. So you select each input and then find out which inputs have, if you change them, a higher effect on the solution. And in this case, we see that basically the background is irrelevant, but the foreground is very relevant because the shape and these points, they kind of make the system believe this is a dog. So we take this connotation of saliency and transform it to our job shop. For instance, in this case, this is just one situation where, as you can see, there's a lot of jobs at machine 4 with a certain waiting time. Machine 7 is about to starve very soon, or machine 1, because there's no job that can use. And we can identify the relevance by the saliency of each individual job and see each of the actions, which allows us to transform it into an almost human interpretable model. Like, if you ask a system, why did you do this next action? It can say, well, look at this machine, it's very important, it's very crowded, there's lots of job, and this one has been waiting very long, that's why I take it here. This is very similar to if you have a human controlling the system, the human will look at this and like, oh yeah, maybe this machine has to care about this. But still, I'm convinced that there's a lot of more research necessary. So just as a short wrap up, we can see that we can have an efficient control of reinforcement learning production control. We can see that we can steer the different targets, what we're looking at, if we have a multi-operization, and we can use explainability to understand some of the parts. With that, I hope that you get some ideas of reinforcement learning and its ability to use it somewhere, and I would love to hear if you apply it anywhere. Thank you.
Thank you.